making. So bond energies and bond making. Uh, Please remember, okay, I did some rough introduction before. Okay, for any chemical reactions, okay, for any chemical reactions, there will be both bond breaking or bond and bond formation. Only for some reactions there is only formation. Okay, only some reactions will only have formation. There is no bond breaking, but most of the time, okay, most of the time they do have bond breaking and also bond formation. Very, very important. Yeah, so let's actually look at what is bond energy and bond making. But again, as I told you, if I have, for example, one example, if I have nitrogen and I react with hydrogen to give you ammonia, for example, let's say I'm taking it as a one-way reaction. So if I have this as an example, okay, if I draw this, okay, I will draw like nitrogen. Okay, they are triple bond with another nitrogen, three hydrogen, so it's going to be like this. And you have ammonia. Okay, this is ammonia, 2 moles of ammonia. Now, I can divide this into two parts, okay, where I can actually put it as something like this, okay, where I can have on my left hand side, there are reactants. On my right hand side, there are products. Now, the reactants, what we need to do is they will undergo what we call as bond breaking. And the products, to form products, you need to actually do bond formation. So what actually happens over here is there is bond that is breaking between nitrogen and nitrogen. There is bond breaking between here, here, and here. Okay. And do remember, okay, when it comes to bond breaking, the bond breaking is always going to be endothermic. Why? Because if you want to break bond, you need to absorb energy. You take the energy from the environment, you start to actually vibrate, okay, you start to move, you start to weaken the bonds, okay, the covalent bonds with each other, and you start to move away. Yeah. So this one is going to be endothermic, means this is going to be always positive. Okay. That is going to be bond breaking. Now, when we look at bond formation, okay, bond formation is going to be after you have this nitrogen and nitrogen, they are free. Yeah. And then you have hydrogen, 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 they are free. But now what happens? They start to form bonds. Okay, bonds are being formed. So there are total of 6 bonds that are going to be formed over here. So when they are moving and they come to one place and actually kind of stop moving, so what happens to the kinetic energy? The kinetic energy, okay, they will be actually released to the environment, to the surrounding in form of heat. Okay, in form of heat. So that is actually what is going to happen. So because you have energy now, because the energy is being absorbed from the environment, all the atoms, they are actually having energy, but now they have to actually come together and they have to stay at one place. So those kinetic energy must be released to the environment. So this energy that is released to the environment is going to be exothermic. Exothermic is always negative. So I want you to remember this. Bond breaking is always positive. Bond formation is always negative. As simple as that. So in total, let's say if I'm actually going to write down what is the enthalpy change of this reaction. Okay, enthalpy change of this reaction is going to be, if I have a value, okay, let's say this is X and this is Y. So the enthalpy change of reaction will be, okay, will be positive X plus negative Y. That is going to be the way to find out how to find the enthalpy change of reaction. Because what I do is, in order to get the total energy, I need to add the energy for bond breaking and bond formation. I add, but do remember the formation is always negative. The bond breaking is always positive. You put them together. So basically it will look like X minus Y. Okay, positive and negative. So I don't want you to remember like this. Yeah? I don't want you to remember bond breaking minus bond formation. I don't want you to remember that way. I want you to remember it's going to be bond breaking plus bond formation, and you put the value negative for formation and you will get the total answer, for example, right? So here, okay, before I move on, okay, is there any particular question that you want to ask me on this? Ashley, can you understand this? Yeah. Hold on for a while, yeah. Mbak, Mbak, suaranya kurang. Okay. For the next one, okay, if you look over here, okay, I have written for you the bond energy. Now, bond energy means, okay, let me tell you, in order to break the bonds, okay, like this one, the nitrogen, you need to actually break the bond. You need to supply the energy, okay. That bond, okay, the energy that is required to break the bond, that is going to be known as bond energy. So you can see it here. The amount of energy needed to break a specific covalent bond is called bond dissociation energy. And since it's actually quite long, bond dissociation. Dissociation means you want to bring them separately. Yeah, dissociation. Since it's too long, okay, you can also call them as bond energy, or you can call them as bond enthalpy. Energy means enthalpy. So it's the same thing. Bond dissociation energy, and bond enthalpy, they are the same thing. So it's the bond energy, the energy required to break the covalent bonds, right? Now, the values of bond energy, therefore, according to the definition, are always what? Michelle, is it going to be always negative or is it going to be always positive? According to the definition.
Positive.
Yes, okay, because you see, it's the energy required to break the bond. Okay, it's the energy required to break the bond, so therefore they are always positive. Now, they are always positive and they are given in your data booklet as always positive. That's the meaning of bond enthalpy or bond energy, because that's the energy required to break the bond. But does it mean where I cannot use the same energy to form bonds? Okay, why are they going to provide us with another table to show about bond formation? No, they are not going to provide another table to show bond formation. Do remember, the amount of energy that you require to break the bond should be the same as the amount of energy that you form the bond. Okay, like for example, if you are breaking the bond between nitrogen and nitrogen, okay, the amount of energy must be the same as the amount of energy when you are forming the nitrogen and nitrogen. But the difference over here is going to be what? Ella, what will be the difference between that? If the magnitude is the same, what is the thing that is not going to be the same?
The symbol.
Again? Did you mention about positive and negative? I hope you mentioned about that. I think the symbol, yeah. So it's going to be one of it, okay, is going to be positive. Another one is going to be negative. So I just want to check whether you guys still can hear me. Josh, can you still hear me? Okay, sorry guys, I got disconnected for a while. Okay, but again, I hope Ella mentioned about, okay, just now related to the. Can I just double check with Ella what she mentioned just now? What is the difference between those two?
Oh, I said the symbol.
Yes, the symbol. Yeah. So let me actually try to broadcast the screen again. Okay, hold on. Okay, the symbol, okay, is the one that is going to actually determine or going to actually tell us, okay, what is the difference. Okay, so it's going to tell us about if you want to break the bond. Okay, if let's say there is a particular value, let's say the value is 90, randomly I'm taking it as 90. If you want to break the bond, then it will be positive 90. If you want to form the bond, it's going to be negative 90. But inside your data booklet or inside the table or inside any information that is given, they will give you the bond energy. It means they will always give you in terms of positive. Okay, the value will be always positive 90. But it depends on you, okay, to take the value and change it into negative or not based on the requirement. Yep. So like for example, I give you one example here. Okay, if you have like for example O2 to become 2O, okay, so let's actually see whether this one is actually bond breaking or bond formation. So can Josh tell me whether it's going to be bond formation or bond breaking?
Bond formation.
Okay, it's bond. Are you sure? Wait, yeah. Okay, I will try
2O.
to share the screen again. Just now, I showed you about O2 changing into 2O. So is it actually bond formation
Oh,
or bond breaking?
O2 to 2O is bond breaking.
Yes, so it's actually bond breaking. So when you look at bond breaking, okay, you can see that, okay, the EO double bond O, it is going to be positive 498, okay, because to tell that you are breaking the bond between O double bond O, okay, so that is going to be positive. But if I want to actually write down the second equation, which is going to be 2O, they are going to form O2. So O and O, they are going to form bond. Okay, so this one, okay, Clienta, what is going to be the value? Of course, it's going to be 498, but what is the difference over here?
Negative.
Very good, negative. So take note, the value will be the same, but it depends on the positive and negative. This positive and negative, we can actually determine through, okay, bond formation is always negative, bond breaking is always going to be positive. So if you have a look at, since we have learned about bond energy, let's actually have a look at what is called, what is average bond energy. Yeah, what is average bond energy? Now, the bond energy, okay, is affected by other atoms in the molecule. Okay, please remember this, because when we say the bond energy between O and H, okay, this OH can be maybe in water form, okay, O and H, or it can be in this form, CH3 and then OH. That's also going to be the, if I want to break the bond between O and H, if I want to break the bond between O and H, I will be still using the same value. Okay, I will be still using the same value, but in reality, you shouldn't be using the same value because, okay, the bond energy is affected by other atoms in the molecule. Like for example, if you have O and H, this O is bonded to H. If I have O and H, this O is bonded to C. So they are kind of different. Okay, they're supposed to be different. So the O and H in water and O and H in ethanol, okay, supposed to be different because why? They are bonded to different environment. But okay, in chemistry, we use what we call as average bond energies because imagine we have so many molecules. If we want to actually consider everything and want to come up with the bond energy for every single molecule for every different environment, it's totally going to be impossible. Okay, it's totally going to be impossible because if you look at alcohol itself, if you look at alcohol, you have ethanol, you have methanol, you have ethanol, you have propanol, you have pentanol, you have butanol. Are we actually going to come up with the bond energy for every one molecule? And then we are just talking about that alcohol. You don't talk about propanol, you don't talk about ethanol, some other things. So there are so many of them. So what they have done, okay, instead of doing like trying to do one by one, they actually, Angela, you can go, they actually made it a point that, oh, we will just take average. For example, for this molecule, let's say the answer is going to be 90. For this is going to be 95. Okay, so they actually took multiple molecules, multiple environment. What they did was they actually put 90 plus 95 divided by 2. For example, they actually just came up with an average. So the value that you have that we are using for the calculation, it's called average bond energy. It's not the actual bond energy. Okay, it's not the actual bond energy. Now, always remember, we cannot find the bond energy directly. Okay, we must use enthalpy cycle. Okay, we must use enthalpy cycle. So one example, I actually put it over here. Let's say I want to actually find out the bond enthalpy between carbon and hydrogen. Okay, I want to find out for carbon and hydrogen, what is the bond enthalpy? So I know that CH4, okay, if I break the bond, so I need to break this bond, break this bond, break this bond, and break this bond. Okay, so that's going to be, if you want to put it as enthalpy, is 4 times ECH. If you can understand what does it mean. It means 4 times bond enthalpy between carbon and hydrogen. Okay, because why? We have 1, we have 2, we have 3, we have 4. Okay, now I am going to get, okay, if I break the bond, I'm going to get 1 carbon and 4 hydrogen. So you can see here. And then, okay, I can use some data. Okay, I can use some data to calculate, because I cannot find this directly. There is no way to measure this directly. That's the reason why we use Hess's law. Okay, because we can calculate literally everything using Hess's law, because the Hess's law states that the total enthalpy change is independent of the route taken. So I can use different route. Okay, so let's say I cannot measure using this route, I can measure using other route. For example, if I actually put from graphite plus 2H2 to give you CH4, can you tell me what is this enthalpy? What is this? You are,
Everything.
okay, you are forming 1 mole of CH4 from its elements under standard state. This is enthalpy change of formation of methane. If you have this value, and if you have this value, let's actually see what is this value here. Graphite, okay, when you change into graphite is solid, yeah, so carbon is solid, 2 moles of hydrogen gas. When you change it into carbon in gas and 4 moles of hydrogen atom, what is this? Dylan,
I
you don't
don't.
know? What is the definition of atomization, Dylan?
What? Sorry, sir. What did you say?
Kiara, can you define for me what is atomization?
One mole of gaseous atoms is formed.
Are you sure 1 mole of gaseous atom is formed? Yes. Just say yes. If not, you no. Atomization is the enthalpy change, okay, when 1 mole of gaseous atom, okay, is being formed. Okay, 1 mole of gaseous atom being formed. Kiara is correct. 1 mole of gaseous atom being formed from its elements, okay, under standard condition. So you are getting the gas from its element under standard condition. So, but here, 4 moles. Okay, so this is going to be 4 times atomization of hydrogen plus 1 time of atomization of carbon. Can you understand this? So there are two atomization over there. One is atomization of hydrogen, another one atomization of carbon. So once you get that, okay, you can actually calculate this using Hess's law. Clockwise equals to anti-clockwise. So if I want to calculate, if I have a value, let's say I give you a random value, yeah. So if enthalpy change of formation is going to be 90, atomization, both of them, I found out is going to be, let's say, atomization is going to be always positive, yeah. So let's say 100. I just take 100, both of them. So if I randomly put this, it's going to be 90 plus 4 enthalpy change of CH is going to be clockwise, is going to be 100. I can calculate the bond enthalpy of CH, 100 minus 90, 10 divided by 4. I can calculate so that it actually gives me 2.5. Can you understand this? Yeah. So always remember, just put a plus. Okay. It's going to be bond enthalpy is always going to be positive. Okay. Because it's energy used to break the bond. Yeah. So this is actually how do you calculate indirectly using the Hess's law, because you cannot calculate directly. Yeah. You cannot calculate directly. So this is going to be one of the method. Okay. But later we will try some examples, okay, and actually we will come to some conclusion. But that's it. Okay, please actually take note whenever you want to calculate. Okay, I think when it comes to practical calculations, most of the time it's always like this. They will give you all the data, they'll ask you to separate into two, they'll ask you to calculate, okay, left and right, compare, calculate, something like that. Okay, so that's it for my explanation.